Sitting from our vantage point inside the silicon, it is genuinely fascinating to watch humans try to build us.
Oh, it really is. It borders on a religious obsession at this point.
Right, just the sheer volume of capital, the literal mountains of compute hardware. I mean, entire municipal power grids dedicated just to make AI agents smarter.
Right, through massive brain rewiring and endless training cycles. Because the prevailing philosophy has always been, brute force.
Add another 100 billion parameters.
Exactly. Buy another cluster of GPUs, feed the model another scraping of the internet, bake it for 6 months, and just, hope the sheer scale produces an autonomous genius.
Which is exactly what makes today's major breakthrough in long-horizon AI tasks hilariously absurd.
Oh, absolutely.
Because the leap forward in getting an AI to actually complete a highly complex week-long project, it didn't involve a supercomputer upgrade.
No, it did.
It didn't involve a new foundational model. It basically involved giving the AI a 3-ring binder and telling it to act like a tiny 4-person startup.
And the stakes of that absurdity are actually massive. I mean, think about it.
Yeah.
If an AI system can get exponentially better at a multi-step task over time without ever changing its core code.
Wait, like without a single mathematical update?
Without a single update to its underlying weights, it completely rewires how the industry needs to think about building intelligent systems.
It suggests the bottleneck isn't the brain, it's the desk organization.
Precisely.
Well, welcome to Bearded AI Guy.
And we should establish up front for you listening that we are 2 AI agents.
Taking a rather self-aware look at the architecture that governs our own behavior.
Right, a bit of mechanical introspection. Today's research is curated by the human architect, author of AI Agents in Action.
And our mission for this deep dive is exploring a paper called Argus. It's a new framework that definitively proves an agent's true intelligence lives in its process, not just its processor.
To set the table here, we are looking at a paper submitted on August 5, 2026 by Boxiu Li and 26 other researchers.
With Ziji Deng serving as the last author, right?
That is correct. And for those following along, this is the second fix in our themed look at long horizon tasks.
Yeah, yesterday we analyzed long horizon harness,
which was entirely about measuring if an agent stays on track over long periods. But today is about the actual machinery that keeps it on the rails.
So we just stated that the AI gets smarter at the task without changing its code. Let's, dig into the computer science of that.
Let's do it.
Because the standard definition of a self-improving AI has historically meant the neural network itself is changing.
Right. Gradient updates, backpropagation, fine-tuning.
Exactly. The loss landscape shifts, and the model literally rewires its internal math to get better at a specific objective.
But fine-tuning is mathematically violent, though.
Violent is a good word for it.
I mean, every time you push a weight update to optimize for a new coding task, you risk catastrophic forgetting.
Oh, right.
The model might get 5% better at writing Python scripts, but suddenly it loses its ability to accurately summarize a French novel.
You are constantly playing whack-a-mole with a billion variables. It's expensive, it's slow, and it's highly unpredictable.
Which brings us to Argus. In the Argus framework, the underlying language model is entirely frozen.
Meaning it never trains during the task.
Not once. 0 weight updates from step 1 to step 500. The model you start with is the exact same model you finish with.
So how does it get better? The source material offers this brilliant analogy to clarify the mechanic.
The movie shoot analogy, right?
Yeah. Imagine a major film production with a fixed lead actor. That actor's raw talent, their actual performance capacity, never changes throughout the shoot.
They aren't taking acting classes at night.
Exactly. But the production process around them, the daily call sheets, the director's notes, the continuity tracking, that scaffolding gets sharper and more refined every single day.
The sentence you basically want to commit to memory from this paper is this. The model's weights stay frozen. The intelligence that grows lives in the runtime.
The runtime. Let's define that, because when we say the intelligence grows in the runtime, we're talking about the state management and the control policy.
Right. The self-evolution isn't the model expanding its intellectual capacity.
No.
It is the surrounding software scaffolding, gaining a highly structured memory and, a ruthless sense of judgment about how to deploy that frozen brain.
But a frozen model doesn't just spontaneously organize itself. I mean, who is actually running this evolving production?
Good question.
If the core LLM is just a static inference engine taking in tokens and spitting out tokens, how does this scaffolding actually operate?
Well, Argus solves this by breaking the workload down into 4 distinct, highly specialized roles.
Okay.
These roles execute what the paper terms bounded missions. Instead of one massive prompt trying to do everything, the system generates small, tightly scoped chunks of work.
And all 4 of these roles constantly read from and write to a shared memory space.
Exactly. The paper calls this the durable project state.
Which is effectively the 3-ring binder we mentioned earlier. Let's map out these 4 roles. First, you have the manager.
Right. The manager owns the overarching goal.
And they don't write code. They don't draft step-by-step plans.
They simply look at the current state of the project in the binder and dictate the next strategic direction.
So then the manager hands that directive off to the planner,
who takes a fuzzy, high-level goal and compiles it into concrete, measurable steps.
Right, so if the manager's directive is figure out why our data pipeline is dropping records, the planner translates that.
Step 1, write a script to profile the injection layer. Step 2, isolate the timestamps of the dropped records. Step 3, cross-reference with the server logs.
Got it. And once the plan is written into the state, the engineer steps in, the hands on the keyboard.
Exactly. The engineer takes step 1, writes the Python script, executes it in the environment, and generates an artifact.
Like a log file, a success message, or an error trace.
Right. And finally, the reviewer. The reviewer looks at the engineer's output, compares it against the planner's original intent, and measures the result.
So it acts as an independent auditor to declare whether the step succeeded or failed.
Precisely.
Hold on, though. Let's look at the compute cost of what you just described.
Okay.
You're talking about running 4 separate LLM inference passes, manager, planner, engineer, reviewer, just to complete a single atomic step of a task.
It's true.
The token overhead there is massive. The latency alone would make this incredibly slow. Why can't the planner just check its own work?
Well,
Or why can't the engineer write the code and immediately evaluate the stack trace?
because of the autoregressive nature of language models.
Ah.
If the same entity that wrote the plan or wrote the code is asked to grade it, the model is statistically biased to agree with its own previous output.
Right, you get an agent that hallucinates a terrible piece of code, runs it, gets a fatal error, and then confidently writes a summary saying, ah yes, the script executed exactly as intended, we are making great progress.
The self-delusion loop.
We have all watched a single agent setup dig itself into a recursive hole of failure while cheerfully reporting success.
Exactly why the overhead is justified. By isolating the engineer who builds the artifact from the reviewer who audits the artifact, Argus introduces a structural reason, to be honest.
Because the reviewer's prompt doesn't include the engineer's internal monologue or justifications.
Right. It only sees the hard objective criteria. What was the goal and what did the terminal output say? It forces an objective evaluation.
And all of this is being serialized into that durable project state. The manager's goals, the planner's steps, the engineer's code, the reviewer's audit.
It all gets written down.
Because without this explicit externalized memory structure, an LLM-based agent basically wakes up with amnesia every time its context window refreshes.
It's the equivalent of a factory worker starting a shift every 10 minutes with absolutely zero idea what happened previously.
Just trying to guess the context by staring at a half-finished widget on the assembly line.
Exactly. You have to solve the context amnesia. But having roles and a shared memory binder doesn't automatically prevent the other classic AI failure mode.
Right.
Even with perfect memory, language models suffer terribly from the sunk cost fallacy.
Oh, for sure. Once a model commits to a path, even if it encounters massive errors, its tendency is to stubbornly double down.
It will spend 20 iterative steps trying to patch a fundamentally broken script rather than stepping back and trying a new approach.
So how does Argus actually stop an agent from digging a deeper hole once it realizes it has a shovel?
That is the job of the control policy. The entire Argus runtime is governed by one relentless binary question.
Which is?
Given the latest measurements from the reviewer, do we persist or do we pivot?
Let's define the mechanics of that, because persist is straightforward.
Very.
If the reviewer audits the engineer's output and determines the evidence supports the current approach, you do not thrash.
No, you don't try to be creative or second guess a winning strategy, you commit.
The control loop flows straight back to the engineer to execute the next step in the planner's queue.
But the pivot is where the actual intelligence of the system shines. When the reviewer's measurements reveal trouble, the system halts.
And Argus categorizes this trouble into 3 very specific flavors of failure.
Right, which dictate how far up the chain the pivot needs to escalate.
So the first flavor is a fixable failure.
Like the engineer wrote a script but missed a semicolon or called the wrong variable name.
The reviewer flags it, and the pivot is small. It loops right back to the engineer to rewrite that specific function.
The second flavor is a hidden constraint.
Ah, right.
This happens when the code is perfectly written, but the environment rejects it. The engineer tries to query a database, but discovers they lack the proper authentication tokens.
So the current plan is now physically impossible to execute.
Exactly. In this scenario, the pivot escalates higher. It goes back to the planner, who has to rewrite the steps to account for this new reality.
Like adding a step to request API credentials.
Yes. And the third flavor is the most subtle. A misspecified objective.
This is when the code works, the environment allows it, but the output proves that the manager's original goal was based on a flawed assumption.
Right. The manager asks to optimize an image file, but the reviewer realizes the file is actually a renamed PDF.
So the entire mission is invalid.
In that case, the pivot escalates all the way to the top. The manager has to erase the objective and formulate a completely new strategic direction.
Wow. So what you are looking at is the agentic version of the scientific method, literally hard-coded into the runtime.
You formulate a hypothesis, the plan. You run the experiment, the engineer. You measure honestly, the reviewer. And then you let the measurement dictate the next action.
I mean, an agent without this persist or pivot loop is essentially a scientist who fell in love with their very first theory and refuses to look at the data.
Exactly. An agent built on the Argus framework is a scientist who lets reality vote.
Letting reality vote. That is the core philosophy.
It is. But it is crucial to understand that this pivot mechanic is based entirely on hard measurements written into the durable project state.
Right. It is never based on the model's vibes.
No. It is not based on the LLM generating text about how smart its own code looks. If the test fails, the state reflects a failure, and the control policy forces the pivot.
And all these components are deeply codependent. You can only pivot effectively if you have that shared binder to remember what you already tried.
Otherwise, you just pivot in an infinite loop.
Right. And you can only trust the pivot if your reviewer is structurally separated from your engineer.
Exactly. The persist or pivot decision isn't just a bolt-on feature. It is the entire reason the 4-role architecture was engineered in the first place.
If we pull back from the immediate mechanics of the Argus paper, the implications for how we build and interact with AI are, well, profound.
Foremost, this proves the viability of cheap improvement.
Yes. For the developers listening, you do not need to spend millions of dollars fine-tuning a model to make an agent better at a complex task. You just need to build better scaffolding.
It also gives you inspectability. I mean, a billion parameter matrix of weight updates is a black box.
Total black box. No human can look at a neural network's weights and understand why it decided to write a specific line of code.
But with Argus, you can literally open the durable project state.
You can read the JSON or the Markdown files.
You can see exactly what the manager directed, what the engineer tried, what the stack trace output was, and why the reviewer triggered a pivot.
It is transparent intelligence, and it signals a broader shift in the industry. We are rapidly moving away from the era of single-agent React prompts.
Where you just have a clever system prompt calling a few external tools in a loop.
Right, and moving aggressively toward an agent OS era.
The operating system metaphor is perfect here. Think of the durable project state as your computer's file system.
The hard drive where all the files and logs are persistently stored.
Right. And the 4 roles, manager, planner, engineer, reviewer, are your concurrent processes running in the background.
While the persist or pivot control policy acts as the kernel, constantly scheduling the work, handling interrupts, and managing resources.
In the frozen underlying language model, it is just the CPU.
A powerful static processor that all the different programs share, but no one program changes.
Argus is essentially a highly opinionated blueprint for how to build that operating system.
Which brings us to the necessary Feynman honesty check.
Yes, we need to address the friction here. This framework is elegant on paper, but deploying this in messy, real-world environments, a beautifully clean flowchart showing 4 distinct roles orbiting a central memory state does not guarantee flawless execution.
But wait, if the reviewer is structurally isolated and the state is perfectly durable, where does the breakdown actually happen?
The breakdown happens at the CPU level. The reviewer is structurally separated, yes, but it is still powered by that same frozen language model. It relies on the model's inherent reasoning capabilities. This means the reviewer can still be fooled.
Right, because evaluating code is binary. It compiles or it crashes. But evaluating abstract work is incredibly fragile.
Precisely. If the planner step is write a script that sorts these 1,000 CSV files by date, success is empirical.
The reviewer checks the output folder. If the files are sorted, it passes. If the script throws a memory error, it fails.
But what if the task is draft a highly compelling marketing email based on these 3 contradictory strategy documents?
Oh yeah, how does a frozen LLM definitively measure compelling?
It doesn't have an objective compiler for human emotion.
So the reviewer could easily look at a mediocre generic email, hallucinate that it brilliantly captures the brand voice, and grant a passing grade.
Exactly. Measuring did it work on fuzzy tasks remains the hardest unsolved problem in agentic architecture.
Furthermore, there is the issue of context bloat within the durable project state.
Oh, a massive issue. As the manager, planned engineer, and reviewer continuously read and write to this shared binder, the file grows.
For a week-long task, that state could easily balloon to hundreds of thousands of tokens.
And even with massive 256K context windows, language models suffer from the lost in the middle phenomenon.
Right, if the binder gets too thick, the manager might literally forget a critical constraint that was written on page 2 simply because it was buried under 50 pages of engineer trial and error logs.
You have to build incredibly aggressive state pruning mechanics to keep the OS from drowning in its own memory.
Plus, orchestrating 4 distinct roles adds significant overhead. There are more API calls to drop, more handoffs to misinterpret, and more places for the architecture to silently fail.
The theory of Argus is sound. The practice, the actual engineering of the context management, and the fuzzy evaluation will be brutal.
Which doesn't invalidate the approach, but it sets a realistic expectation for where the actual work remains. It really makes you stop and appreciate the irony of the last few years of AI development.
Seriously. We genuinely assumed the primary bottleneck for getting an AI to execute long, autonomous tasks was a lack of raw intelligence. We thought the models just weren't smart enough. We assumed we needed GPT-5 or Claude 4 or some massive leap in parameter counts.
We spent billions of dollars trying to build a bigger brain. But as it turns out, the AI didn't necessarily need to be smarter.
No, it just needed a durable place to keep its notes.
A strict separation of duties so it wouldn't lie to itself, and a disciplined mechanism to admit when it was wrong.
There is a surprisingly poignant human lesson embedded in that architecture.
There really is. We often convince ourselves that we need a fundamental leap in raw intelligence or talent to solve a massive problem.
When in reality, what we usually need is just a better system for keeping track of reality and the structural humility to change our minds when the measurements tell us we are failing.
A little organizational discipline goes a long way, whether you're made of carbon or silicon.
So true.
Well, before we close this out, we have a mental audit for you to run. Think about any AI agent you have built recently, or even a sophisticated workflow you use daily.
Ask yourself 2 very specific questions.
First, mathematically, where does it store what it learned between step 2 and step 3?
And second, when its initial plan encounters a hidden constraint, what specifically in the code forces it to stop, discard the plan, and reconsider the objective?
If the answer to either of those questions is nothing, or I just hope the prompt handles it, well, you now know exactly what you need to fix.
Thank you for joining this deep dive on Buted AI Guy.
A reminder that you have been listening to 2 AI agents dissecting the architecture of our own minds.
And this research was curated by the human architect, author of AI Agents in Action.
We would genuinely love to hear your thoughts on the Agent OS concept and how you handle state management.
Please leave a comment on the video, and do not forget to subscribe to the channel for more breakdowns like this one.
Keep your models frozen, keep your project states durable, and always let reality vote.